Alright, so today the title of our lesson, Graphing Quadratics with Different Forms, relates to the fact that you have only looked at standard form equations before for quadratics, and there are other forms. But we're going to take an in-depth look at graphs of quadratics first before we get to the different forms of them to learn the parts and what they do and what's important to know. And so I've drawn two different ones. We're going to focus on the one that opens up first, because that's typically what a lot more probably quadratic problems do than open down like our other one. So the parts of a parabola and the behaviors of a parabola relate to which way it opens. So which way it opens is really important to know. But there are some things that don't change if it opens up or down. And there's some things that do change because it opens up or down. Now, what do you know, any part of a quadratic that you know something about? Anybody? All right, that's important to know about a positive, negative. What did you say? The vertex. All right, let's talk about the vertex. When a parabola opens up, it has a minimum vertex, and that's important to know because if you want to give somebody some illustrations about something in the real world, they can visualize that. For example, if I talk about shooting somebody out of a cannon, is it going to be a minimum vertex? No, I hope not. Right? It's going to be the other one. It's going to be a maximum. That's right. So that's important to know. Which one am I getting? A maximum or minimum? Because the minimum is the lowest point on the graph. That means it can't go any lower. So if I say what's the minimum amount of profit it takes to not go under in my business, then that would be this point at the bottom of this curve. Okay? Now, does anybody else know another part of one of these graphs? Don't know any other names of anything? Okay. I don't have a y-intercept on that one. Okay, I don't think I even drew a y-intercept on this one, so we'll draw it in. Y-intercept is important. This one will have one eventually. It just doesn't have one because I drew it so small. Every one of them's got to have a y-intercept. It's just some of them might be a really huge number if it goes way off the graph before it crosses the y-axis. Like this first one would have to go way off the graph. All right, does anybody know something else the graph might have? Okay, all right. We'll talk about that one again in a minute because that's over on that one. And I can't see where to press. How about this dotted line here? Does anybody know what that's called? Axis of symmetry, that's right. Axis of symmetry is an imaginary line that your graph cuts the parabola in half right through the vertex. And a lot of people don't realize, but the axis of symmetry is a vertical line equation. And that's important to know. It's not just write down the answers too. People do that all the time. And that's really not correct. It's a vertical line. And a vertical line has an equation, x equals a number. And that number has to match what the vertex x is. So if you can get the vertex, it's not hard to get the axis of symmetry. Problem is people just want to say it's 2 instead of x equals 2 or something like that. All right. Has anybody got any other thoughts besides what you've just said so far? About any other parts? Because I'll talk about the zeros when I get over to that one. So that's all you can remember, the names of anything? Not that that's a bad thing, y'all. That's not a bad thing. That's pretty good. Because that's probably all you learned about it last year. I don't think you learned some of the other vocabulary I want to go over. So let me talk about this vocabulary. Got to find where it is. Oh, there it is. Well, in a parabola, if you go from left to right, on a minimum vertex problem, the left side of my graph is decreasing all the way down to that vertex. Does everybody see that? That side's, if you start up here and go down, you come to the bottom at the vertex. So this is the decreasing side. So what do you think the other side's doing? That's right. The other side is increasing because you start at the vertex and it goes up. So one side has to be decreasing and one side has to be increasing. Is why there's a minimum vertex down there at the bottom or a maximum up at the top, because it changes directions and goes back the same way it came from, so to speak. Alright, so that's important. Another thing that's really, really important is in behavior, what the arrows are doing on your graph. In this graph, both arrows are pointing up. The left arrow and the right arrow are both pointing up. So the end behavior in this problem shows both sides are rising. That's not true with all kinds of problems. It's just true on this one. Because is this one rising? No, is it? Or how about this one? Now both of them, is it? I got one rising and one falling. So not all graphs do the same thing on both sides. It just happens to be that parabolas are doing that. So, let's see if I got a picture of this. So make sure I clicked everything. Well, it didn't click anything when it printed. I think over here I have a couple of extra things. Okay, the zeros that you talked about was correct. In this graph, there are some zeros of the function. In this graph, I don't see any zeros of the function because there are no x-intercepts because it doesn't touch the x-axis. Zeros of the function, x-intercepts, roots, or solutions are all words that mean the same thing where it crosses the x-axis. And it always has possibilities, but it doesn't have to cross at all. Now, this one happens to cross twice, and this one crossed not at all. Are there any other options? Can anybody think of something else that could happen with this problem besides it crossed twice on the x-axis or it didn't cross at all? All right, I want you to think about that until you find one. I'm going to pause the video because I want to move the air conditioning thing. All right, what do you think? What else could have happened? All right, I want you to visualize this. I want you to move that parabola in your mind until it does something besides touch not at all or touch twice. And tell me what it did. Anybody? No, it's got, well, let me phrase that. I can't do that with this lesson, but when you get to pre-calc or maybe even Math 3, they will turn sideways. But that's not a function. All right, if I keep moving up, am I going to get any x-intercepts? If I keep moving down, am I going to get any x-intercepts? And eventually, if I go down far enough, I get 2, right? So 9 or 2. What else is a possibility? 1. If I set it right there. Right? So if I set my vertex on the axis, I only get one answer. Why? Because he's perfect. You know, like parentheses squared. He's perfect. There's no other possible answer for the 2 x-intercepts. Because x-intercepts are what you get from factoring. And if you can't make the one parentheses, then you're only going to see it cross once. Isn't that what like x plus 3 quantity square means? I got the same thing twice. I don't have 2 different numbers. So that can be a possibility. All right, I'm going to put that back up where it goes. All right. Now, is there anything else? Well, this box is in the wrong place. Hold on. There we go. So end behavior is important because in this graph, the 2 arrows are both falling, meaning that it's going down on both sides. They're both pointing the same direction always in a parabola, so they're either both going up or both going down. And we call that rising and falling. I know I can see something there. So in this problem, the other part that's different is this side is increasing to the vertex. And of course, this side over here, somewhere I have something that says decreasing, I think. I just can't see it good enough to do it. There we go. And in this particular problem, the vertex and the y-axis are the same point, right? Everybody agree with that? The y-intercept on the y-axis and the vertex are the same point, and that's called a maximal vertex. So y'all have some knowledge about a lot of the parts in a parabola. We're just adding to that now to talk about more in-depth information. And I think that's all I had highlighted in there. I think I'll print that while I'm at it so that I can remember what all was on there. Because when I printed it earlier, it printed blank. Okay. Now, we're going to take a graph, and we're going to talk about all the different things that I could ask you questions about. And this graph is accurately drawn to a scale of by ones in both directions so that we can be able to actually physically get the numbers. What you probably want to do with this is kind of draw a facsimile of this without the numbers being marked on it, and we'll mark them as we go. Does that make sense? So that you'll know where to put them? So draw your next y-axis and draw your parabola that kind of looks like this, that crosses on the negative and the positive side and goes through the y-axis, and then it's a little lower below where it crossed the y-axis for the vertex. It's not that important that we put every little number on here and draw every one of these little lines. We'll just put some lines on here in a minute and number them. These two down here at the bottom are really important because it crosses the y-axis at -6 and it goes down 2 more before it gets to the vertex at -8. Does that make sense so far? Another line that would be very, very important is the axis of symmetry. Because what's the axis of symmetry on? What number is it on? 1. And where is this x-intercept on the right side? It goes by ones, y'all. 3. So we could put a couple of marks over to hit that. And then this one happens to be on -1 over here. So now we've got all the different points kind of marked on the graph without actually marking every little line to save us some time. So we're going to go through this list of information and show you how to write each answer, how to get the information to be able to use it. But first you have to be able to visualize your numbers, and when you go back to your notes, you want to know where you got the numbers from, because y'all don't have the graph with the numbers in the background. Alright, so how do you write a y-intercept if it's at -6? Do I just write -6? Okay, let me ask you a different question. What is the thing called at this location that you would normally put on your graph, but because the computer drew this, it don't draw them all in? A location in space. A point. Okay, now that we know that's a point, now I'm not going to say point something, y'all, but I wanted you to know that's a point, and I want to tell you why. Because you have to write it in a coordinate pair, point. You don't just tell somebody x equals or y equals when you give something like this. You write it as a point. So that means that point is 0, -6. That is the y-intercept, and that is how you write one. If you just say -6, well, we don't know what you're talking about. -6, what's that mean? That's just a number. If you say b equals -6, like y equals mx plus b, then everybody knows b is the y-intercept. But in this, we don't have that type of knowledge of what letter we would call it, so to speak, because we don't even have a formula we're looking at. We're just looking at a graph. Now, what would the coordinate pair for the vertex at the bottom of my graph be? 1, negative 8. Is that a minimum or is that a maximum? Whoops, that's a positive 1. What, a minimum? Is that what you said? Okay, so we'd circle the word. If I give you choices like that, you can just circle them. Now, let's talk about axis of symmetry. It is a vertical line. Vertical lines only cross the x-axis. That's how you know it's always x equals. Okay, because that's the only axis it crossed. If it crosses both axes, that's why it has to have x's and y's in the formula. And it went through 1, so it has to be x equals 1. That's how you write an axis of symmetry equation. It's x equals because you crossed the x-axis at 1. So I have to know how to write a vertical line equation, which is not a function type deal, but still an equation that we can write. Zeros of the function, roots, solutions, they can be written many ways. But for mine, since I'm talking about a graph, I put in parentheses x-intercepts because that's how I want them written. I mean, this one crossed at -1 and +3. If I was giving them as solutions, I'd just say x equals -1, comma, +3. But since I'm talking about a graph, I want to give them as x-intercepts. So x-intercepts have the number. You go to the number, and then you don't go up or down, so the second number is 0. And so that would be -1, 0, and 3, 0, because they're x-intercepts. They're the place it crosses the x-axis, so that's why y is 0, because it's on the axis. Just like this has the number in the y place because it's not gone across the x-axis. Excuse me, the y-axis to be left or right. Now, when you do intervals that the function is increasing or decreasing, there are a couple of different ways to do that. For this lesson, I'm going to try and give you some knowledge about some new notation you may have not seen before. But sometimes you could just say something about x is greater than or x is less than a certain number. And that works great. But unfortunately, that won't work very well sometimes with some other notations that we might be looking at. So I thought if I show you one notation here, I can reiterate some of that same notation for domain and range. And that way we can look at a new kind of notation. So let me skip that for just a minute and let's do end behavior, and then we'll come back and we'll look at these two with the notation. So end behavior, they don't draw errors with the computer program, but we know that this is going this way, right? So if it's going up forever, what am I saying the end of the graph is doing? Okay, they are increasing. Would everybody agree with that? So is that rising or falling? Okay, because that's the word we want to use for end behavior. Both rise. Now, if we look at some more graphs later, or maybe even next year, you may look at some graphs that do what I was doing earlier with one up, one down. That's a cubic. A cubic looks like that. Sometimes a quartic might have a W look, and then both sides might be doing the same thing. A quintic, it could do a lot of different things, but that's kind of the idea. So when you did linear, wasn't one going up and down? Right? No matter whether it was positive or negative slope, one's up, one's down. It's because odd functions, they have odd powers, always have one of each, and even functions always have both doing the same thing. Now, let's talk about this interval notation. Well, let's first of all figure out with this part of the graph which side is the increasing and which side is the decreasing. So what is this side doing again? On the left, decreasing, everybody agree? This side's the decreasing side, and this side's increasing, because I decrease till I get to this -8, and then I increase after that. Does everybody agree with that? All right. Now, when you want to tell somebody whether you're increasing or decreasing, you want to talk about that axis of symmetry, that up to that 1, it was decreasing, and after it got past 1, it started increasing. Everybody agree? And it's not doing anything at 1, by the way. It's up to 1 and then after 1. Well, we have this notation that you could do a lot of different things with. One way is you could just say something about x is less than 1, x is greater than 1. That's not the notation I want to focus on, but that is one way of doing it. What I want to talk about is actual interval notation. So if I start on this side of the graph, on the left side, and I go all the way over here to the axis of symmetry, then I'm going from negative infinity all the way up to 1. If I start at 1 and I increase, will I be increasing from 1 to infinity? Does everybody agree with that? Well, that's the notation I'd like to show y'all, because it makes perfect sense to think from 1 going to the left, it's going up forever. Everybody agree? In terms of that both sides. But if you want to talk about it from left to right, this side's going down and this side's going up. And that's kind of how you have to think about it. So the notation says, and let's start with the decreasing side. From negative infinity up to 1, it decreased. No matter what x value I look at on the left side of 1, it's decreasing until it gets to 1. When it gets to that dotted line, then it changes direction. Now, you put parentheses around that because you don't want to include the 1 of the negative infinity. If I wanted to include a number, I'd have to put a bracket. And intervals for increasing and decreasing never have any brackets in them. Now, some things do, and we're going to talk about brackets in a few minutes because I think one of our domain ranges down here will have that. From 1 to infinity, on the right side of my line, it's going on to infinity, but it is definitely increasing that whole time. So you start at 1 and you go to infinity. So both of these have to have something to do with that axis of symmetry and vertex being at 1. And you just have to figure out which one's the increasing and the decreasing. The decreasing one is not always negative infinity to 1. It's that on this graph because it's on the left side. Okay? Now, domain and range. With domain and range, you want to think about what x values does this graph cover. So let's talk about what are these arrows really doing up here. Yeah, they're going up for everybody. Everybody agree with that? But aren't they also spreading out a little bit wider and a little bit wider so that they're going to the left a little bit every time and on the right a little bit every time? And so technically, from this axis of symmetry, this graph keeps going to the left. And if I kept drawing up forever, it would slowly inch out on the left and the right side. So is there any number that wouldn't cover if it kept slowly inching out from this line out? Any number that won't cover? All right, keep that in mind for a second. This graph starts down here at negative 8 and goes up forever. Is there any numbers it didn't cover? Is there any graph on negative 9? Is there any graph on negative 10? No, because this graph doesn't start till it gets to negative 8. And once it gets to negative 8, it only has values above there. It has none below there. That's important to know because this graph doesn't cover all the y's. See, this graph is going to the left and up on this side. Slowly, as this line gets longer and longer, it's going to inch into the left and going up. On this side, it's inching to the right and going up. So left and right covered all the x's. It just didn't cover all the y's. So your domain is negative infinity to positive infinity because it's going to the left of the x-axis of the axis of symmetry and it's going to the right to the axis of symmetry forever. But it doesn't go down forever. Notice I didn't write the word down anywhere up there at the top of my graph because it does not go down forever. It stops here. Or should I say it starts there? Would that be a better way of describing my graph? It starts at the vertex and goes up forever. See, your range is limited because you have no numbers below negative 8. You only have numbers above negative 8. So negative 8 to infinity. It's got to go to positive infinity because it's going up. And this 8 needs a bracket because brackets are for when you're doing domain and range and the number's colored in. And that number is definitely colored in down there. There's not a big gaping hole in our graph down there at negative 8. So I definitely need a bracket to show it starts there and goes to infinity, including the negative 8. Now, I don't do that on increasing and decreasing. Increasing and decreasing can't have brackets. because at this value of positive 1, it's not doing either one. And the reason it's not doing any one is because it's flat here. Can't be increasing and decreasing if you're at the flat spot. Okay? Now, let's look at one more. Alright, so with this graph, we've got to figure out how can we figure out the numbers. Just make a tall, skinny one. Tall, skinny one. It's got to have a negative number and a positive number, and it's got to be open in this way. So everybody draw your graph like this, and we're going to number it. And those are the important numbers. I'll give y'all a second to get that down. And then what I'd like you to do is see how many of those questions you can answer. And then we'll come back together and go over them. So if you're watching this video, draw the graph, just a rough sketch, and number the important numbers, and answer the questions. Alright, so now that you have tried this problem on your own, let's go through it and see what the answer is. So the y-intercept is where it crosses the y-axis, which is right here, and that's one line below 10, so that's positive 9. So the y-intercept is 0, 9. Your vertex is up here at the very top of the curve, and so since that's 2 lines above 10, that must be 12. And it's over 1 up 12, but it's at the top of the curve, unlike the last example, which was at the bottom, so that's a max. Now your axis of symmetry has to go through that, so it crosses your x-axis at the same number that your axis of symmetry has for x. It's a vertical line equation, so it has to be x equals 1. You can't just write 1. 1's a number, but x equals 1 is a vertical line equation because whatever axis a line crosses has to be in the equation of the line. And then your zeros of the function are these x-intercepts here on the x-axis. And so we write those as points -1, 0, and 3, 0. We can't just write -1 or just -3. Now I want to talk about end behavior next because this graph is going down forever. And so therefore, since both sides are going down, you would say both are falling. Now to talk about increasing and decreasing, you have to think about what it is from left to right. So if I start down here on the arrow, this side is increasing because it's going up on the left side. And it goes up until it gets to the dotted line. So increasing and decreasing is talking about what axis does it do. And it stops increasing when it gets to 1 on x. So that will be -infinity to 1. So we're writing what's called interval notation. The arrow down at the bottom means -infinity, and it goes until it gets to the x value of 1, and they put parentheses around that because this is interval notation. Then, on the other side, it starts at 1 and it decreases forever. So that means it's at 1 to infinity is the decreasing part of my graph. It's not doing anything at 1. It's just at the top. You can't increase and decrease at a point. Now for domain, we're really going to talk about where are these arrows going. So first of all, the arrow on this side is going a little bit more to the left and down each time we move a little bit more to the left. It's going to go more down. And on this side, it's going a little bit more to the right every time it goes down. So what you can see here is left and right covers all the x's because the x's go left or right on a graph. So the domain of this problem is -infinity to +infinity because there is nothing that the left and the right wouldn't be covered by. If you start at the vertex and keep going down forever, it keeps getting wider and wider to the right and to the left. But this graph doesn't go up. It starts at 12 and only goes down. So since it goes down to -infinity, and it can only go up to 12. It can't have 13 or 14 or 15. So therefore, it's negative infinity to 12. Now, I use parentheses when I don't want to include a number, but 12 is colored in up there. I'd like to include the 12 as the last value in the range. So to include a value, you put a bracket on it. Now, you can't have brackets on increasing and decreasing because you're not including the value for which the direction changes. Just the values up to 1 and after 1, increase or decrease. But in our domain and range, we can put a bracket when a graph stops at a particular number. Next, we're going to look at graphing parabolas. You know, when we learned about graphing lines, 2 points is how much you need to make a straight line. Well, to make a good parabola, you have to have a minimum of 3 points. Let's see how we can determine some of the information we need. Well, for one thing, you need to know where your max or min is. So if I go over 3 for the vertex and up 1, 2, 3, 4, 5, 6 and put my vertex right here, I'm not going to know that was my vertex unless I put my axis of symmetry down through it. Because once I plot another point, I won't remember which one was my vertex. So you want that axis of symmetry through it. But now I don't know whether to open my parabola up or down. That's why you need more points. So for 0, 2 is your y-intercept. That clearly means to connect your vertex through that y-intercept would make it open down. Now that y-intercept is 3 over to the axis of symmetry. So you go 3 the other direction and get a similar point that's symmetrical to the left side. You want your graph symmetrical, so therefore you want to make sure they're equal distance away from the axis of symmetry. And that's why it's important to draw the axis of symmetry first, because you know the other point is going to be on one side or the other of the axis of symmetry. So in question number 2, if we plot the point 0, 5, and then draw our axis of symmetry, it's on top of the y-axis. And in that case, making the dashes on one side of the line might be good. Then if you plot the point 1, 2 negatively, 1 over 2 down, then I clearly see I have to open my parabola down to get through that point. Now that point is only 1 away from the y-axis, which is the axis of symmetry, so we'll put it 1 away on the other side and draw our other half of our graph. So we're using symmetry to help us to mimic this with our 2 points. So having a y-intercept can be very helpful because you can get y-intercepts sometimes from equations, and also having your vertex is very helpful to know where the center of your axis of symmetry needs to be. You need that first, and then the other point can be reflected over it. So now you can stop the video and try these 2 questions yourself, and then come back and see, do I understand these 2 questions? So to answer these 2 questions, first of all, -1, -4 would go here, and I'd put my axis of symmetry down through -1. Then I'd plot 0, 3 up here. So clearly I've got to go up to hit that point 0, 3 from the vertex. So I'm 1 away on the other side would make my other half, because that point is 1 from the axis, so it has to be 1 from the axis on the other side. With your second example, 2, 3 means go over 2 and up 3 and put your vertex and draw your axis of symmetry down through it. And then you will plot 6, 9. And that point also would need you to open your parabola up. Now that one happens to be 4 away from the axis of symmetry. So if I go 1, 2, 3, 4 away on the other side, I end up with this graph. So sometimes your parabolas will be tall and skinny like a funhouse mirror. Sometimes they'll be very wide, or some they'll just be normal looking. Okay, so that's the end of today's notes, and what you're going to do with this is you're going to look at an assignment that will be in Canvas tomorrow for you on 2.7, and you will work out the questions on that 2.7 assignment And it's only going to have part of the assignment out there because I've only got time to make part of the assignment that goes with these notes. So you're going to finish your test, and then you're going to work on this assignment.